Hello, everyone. The unit for these next 2 weeks that we're going to be covering is work and energy. Okay, these are the four sections that we're going to be covering over these next couple of days. Section one is going to be for days 1 and 2. These are going to be 3 and 4, 5 and 6, and this is going to be 7 and 8. And then 9 and 10 are going to be your assessment days. Okay, so we're going to start off in section one. Section one is for day one and for day two. So section one of work starts off with this slide asking you to list 5 examples of what you would consider to be work. The purpose of this slide is to get you to give your understanding of what you believe work to be, and then to relate that back to the physics component. So most people, they would consider their job to be work. They would consider any chores that they have to do to be work. And some people relate it to physical activities, anything with the physical exertion. Some people would call that work. Some people would say that, the writing on papers, doing homework is considered work, but some people would say not, since you're, standing still, you're not really doing any physical exertion. So some people relate it to that physical exertion and energy being spent. In physics, the physics definition of work is just the amount of force you put into something times the distance or displacement that it ends up going. So if I'm putting 10 newtons of force and something moves 10 meters, 10 times 10 would be 100. That would be my work. And that would be in joules. Okay, work and energy have the same unit, but they're derived in different manners. But energy is for days 3 and 4. We'll get there when we get there. But just know that work and energy have the same unit. Okay, it's going to be joules, but they represent different things. But they both are units of energy, if that makes sense. So again, work is just force times displacement, and they're saying how much work is 1 joule. So if W is equal to 1, you can have F and D be a variety of things, but this is just one example. If you lift an apple 1 Newton from the floor, a distance of 1 meter, 1 times 1 would still be 1. So this is just an example of how much work is 1 joule. So some nuances. Work. You only do work if the force you're applying is related to the direction of displacement. Now, that sounds a little confusing, but basically, pushing this car would be considered work because the F, the force, and the displacement are in the same direction. So he's pushing to the left, the force is to the left, but also the displacement is also to the left. So because the force and the displacement are in the same direction, this is considered work. And now here are some examples where you're not doing work. So let's say a student holds a heavy chair at arm's length for several minutes. So you holding something up, you're holding something up. So in this case, what's pulling the chair down? What's pulling the chair down is gravity. Oh, that's a bad color. Let's pick red so you can see red. So what's pulling the chair down would be gravity. So the student is doing what? The student is holding the chair up. So in order to hold the chair up, the student has to be putting a force up that matches that force of gravity. So this is what the student is doing right here. This is the force the student is applying. But if the student is holding the chair still, that means there's no displacement. If there's no displacement, D is 0, and if D is 0, you don't have any work. Okay? So that's why this first one's you're not doing any work. In the second one, you have a student carrying a bucket of water along a horizontal path while walking at a constant velocity. So again, we're holding something up. So the student, here you have a student, okay? The student is walking, and when you're walking with bags or something, you're carrying something, you typically hold it at your waist, right? You're just walking with the bags at your waist. So the bags are not going up or down. They're just staying in one spot at your waist, right? But what are you doing? You're holding, let me just put the arms out for the sake of having the bucket or being able to draw the bucket. So you have this bucket filled with water. You're holding that bucket up. So the force you're putting, so gravity is pulling it down again, right? You have Fg. So you have to match that force. So in order for the bucket to stay at the same height, you need to match that force, okay? So this is what the student is doing. The student is putting a force up, but at the same time, the student is walking, but the student is walking horizontally. So the displacement is in this direction. So the force is up, but the displacement's to the right. The force and the displacement are not going in the same direction. Because the force and the displacement are not going in the same direction, you would technically have zero work. And this leads to the next slide, which actually gives you a new version of the equation. So when the displacement and the force do not match directions, you need to do some modifications. So this is where now you add this cosine theta piece, okay? So your new equation is going to be, instead of just W equals F times D, now you have F times D times cosine of this angle, okay? Then if you remember from the unit circle, cosine of 0 is 1 and cosine of 90 is 0, okay? So at 0 degrees, this is 1, okay? At 0 degrees, this is 1. At 90 degrees, this is 0, okay? So if the F and D are in the same direction, like the exact same direction, that means the angle is 0. Okay, so if the F and D were on top of each other, this angle would be 0. And if the angle is 0, cosine of 0 would just be 1, and that part would go away, and you would just get F times D. You would get this equation. So technically, this equation right here, W equals F times D, is only true if the force and the displacement are exactly on top of each other. Okay? That's when you get that equation. But other than that, you have to include the angle. Okay? So in this case, whatever this angle is, that's what you would plug in to this equation. So F times D times cosine of whatever that angle is. In this case, in the case of the bucket, the angle, these two things will be perpendicular. Okay? If they're perpendicular, you have this, and so this would be a 90-degree angle. If you have a 90-degree angle, cosine of 90 is 0. Because if cosine of 90 is 0, anything times 0 becomes 0, so then you don't get any work. Okay? So that's where that comes from. Okay? So if you're at 90 degrees, you're perpendicular. That means you're in completely opposite directions and you're not doing any work. So that's how you use that equation. Okay? Work itself is considered a scalar. Okay, so force is a vector and displacement is a vector, but work is a scalar. Okay, so I'm not gonna get into specifics, but like a vector times a vector is gonna give you a scalar. Okay, and a vector times a scalar is still a vector. There's rules and stuff like that, but you don't have to worry about that. But they're just saying that work is a scalar. Okay, work itself is considered to be a scalar. And work can be positive or negative. Okay, it depends on basically the direction. So If you're going to the right, it's considered positive work. If you're going to the left, it's considered negative work. It's basically, I don't. It has to do with the force. So, in which direction are you putting the force? So on the right side, the force and the displacement are in the same direction. This force, even though it's at an angle, it's going to the right. And this, you're pushing from behind, but it's still going to the right. So it's positive work. In this case, we're pulling to the left, but the displacement is still going to the right. So in this case, the force and the displacement are in opposite directions, so you have negative work. Okay. So if the force and displacement are in the same direction, like they're both going to the right or they're both going to the left, it's positive work. If they're going in opposite directions, you have negative work. That's what it's saying. And here's a quick classroom example. A 20-kilogram suitcase is raised 3 meters above a platform. How much work is done on the suitcase? So first we need to calculate. So we would have, so let me write the equation again. W is equal to F D and then cosine of our angle. Cosine of our angle. Okay, this is F times D times cosine of the angle. Pardon the sloppiness. So a 20-kilogram suitcase is raised 3 meters above a platform. Okay, so in order to lift the suitcase up, we need to put a force going up. And the displacement is also up. We're raising it, so we're going up. Okay, so your F and your D in this case match perfectly. They're both going in the same direction. So because they're both going in the same direction, you can ignore, or not ignore, but you can skip the cosine piece. So if it's 0 degrees, then cosine becomes 1. If cosine becomes 1, then you can just leave it out. So in this case, we have W is just equal to F times D. So what is the F? The F that we need depends on how much the suitcase weighs. Remember, weight is Fg. And Fg is just equal to Ma. So in this case, our mass is 20 kilograms. And then what is that gravity due to acceleration? Okay, this would be Ag, which should be times 9.81. So 20 times 9.81 is going to give you Fg. The Fg is what you plug in here for your F. And then the displacement is 3 meters. Okay, so D is equal to 3. So that's what you plug in here for D. So they got 590. They most likely also rounded this to 10. So they probably just rounded 9.81 to 10. Okay, but to answer this question, you would do whatever you get here, the 20 times 9.81. That'll be your force that you need to lift up the suitcase. And then multiply that by your displacement, which is 3. So whatever you get here, your answer is going to be 20 times 9.81 times 3. Okay, so that's how you get whatever answer they got here. If it doesn't match exactly, it's because they probably rounded something. But that's how you would answer that question. And I believe that's the end of section 1. Okay, it is. So this is the end of section 1. And now it says, based on the physics definition, list the 5 examples you would have done in the last year that you would have considered work. So this is just asking you to basically finish wrapping up your thinking goal. And now I'm going to go through the work practice problems. So day 1 and day 2 are both going to cover work. The day 1 stuff has the key with it already, so I'm not gonna go through that one that has the key for you to practice with. So I'm gonna go through the one that doesn't have the key and give you an example. Okay, and I'm gonna do the last two, since the last two are gonna be the hardest two.